Okay. So, well, Anamaria Gkini. She studied physics at the Aristotle University of Thessaloniki, and she did her master's in astronomy, astrophysics, and mechanics at the Kapodistrian University of Athens. And now she's doing her last year of PhD at the Stockholm University. And she will talk about the eruptive mass loss before superluminous supernovae.
Yeah. Thank you, Maria. And thank you for having me here in the same room where I gave my very first talk 2 years ago. And today I will talk, as Maria said, about eruptive mass loss in superluminous supernova, which is the topic I spend most of my time in during my PhD. And I'm supervised by Dr. Angel Lunan and co-supervised by the, Professor Jesper Solerman. So I can imagine that maybe some of the words in the title maybe are a bit unknown to you, but I hope that at the end of this talk, you will be able to understand something more. So we'll start with a very brief introduction about supernova. So many years ago, almost 1,000 years ago, people start looking in the sky and start noticing that there are some new bright spots that they were there before. And they try to understand what are these new spots that they appear suddenly in the sky. So here I have put 4 images of 4 very famous galactic supernova, which means supernova that happen in our galaxy. And Tycho Brahe's one is the, or however it's pronounced correctly in Danish, is the last one that we observe in our galaxy. So the way that we observe supernova, or the way that we observed supernova 100 years ago and now has changed a lot. So less actually than 100 years ago, we were taking photos of the sky, multiple photos of the sky, and try to compare the photos and try to see if there is any new spot appear in the photos. However, you can imagine that this requires a lot of time and many people as well. They really good to have very good vision in order to understand what is really going on. So now with the development of technology, we have the CCDs, we have the computers, machine learning, and all these tools that we use now. We have surpassed this, and we are able to observe hundreds of transient objects every night. And yeah, yes.
But online they cannot see the...
Me? Probably not. Sorry. Okay. Now? Should be able.
Yes, we can see the slides.
Okay, great. Sorry for
Thank
that.
you.
Okay, yeah. So nowadays we have the time domain surveys, which are surveys that they scan the night sky with a high cadence every night or every 2 or every 3 nights, depending on the survey. And they try to find not just supernova, but in general transient objects, which mean objects that they are in the sky for a specific amount of time and then they disappear. So some of them are the LSST, which this institute is also part, and the Dark Energy Survey, in which this institute is also part. And there are also the ZTF and the Assassin, Pan-STARRS, Atlas, and some other as well. So, okay, we detect supernova, but what do we really detect? So these surveys, they scan the sky and they compare these new images that they have taken with reference images, which they took when they first started. And they subtract these 2 images and they take a look in the difference image and they try to see if there is any bright spot and to measure the brightness of this spot. And this happens because we want to construct the evolution of this brightness with the time. And this is called light curve, as you probably know. So the light curve of transient events and supernova have a particular shape. It has a rise, a peak, and a decline. However, this is not enough to tell us that what we see is a supernova. In order to classify an object as a supernova, we need its spectrum. So there are dedicated surveys that they try to take spectra of objects that they think are interesting. And 2 of them that I mentioned here is the public ISO spectroscopic survey of transient objects, where this institute is also part of. and the Pride Transient Survey, which I am part of in Stockholm. And I have actually observed for both of them, trying to find a classified supernova. And in the right plot, you can see in the right for you. In the right plot, you can see an image of the sky, which was made in October 2024. And I found this from the transient name server, which shows all the supernova that have been classified so far from the different surveys. Of course, you can see that there is a gap in the galactic plane. And this, as you can imagine, is because we cannot really see what is going on due to the dust and everything that's going on in the disk. Okay, so we have found a way of finding supernova. So we need to really understand now what is going on and what we are really looking at. So the focus today will be on the core collapse supernova, in which are explosions of massive stars. And so we have a star, the star burns hydrogen in the core. So when this hydrogen depletes, then the core contracts, the density and temperature increases, it starts fusing heavier elements. And this process is going on in a star more massive than 8 solar masses until the formation of an iron core. And that's why we have this onion-like structure in the star. Okay, this is the ideal scenario. Of course, there are much more complicated, many more complicated things that happen in a star. So this iron core cannot fuse further because it doesn't release energy, but it needs energy. So the iron core collapses. Again, many things are happening during the core collapse that is not really my field of expertise, but what we care about is that we have the launch of a shock wave. And when this shock wave reaches the surface of the star, then the star explodes, expelling the outer layers. And there is where the observers start seeing that there was a supernova happen in that part of the sky. So what we see is not this star, but it's more like this. There is a compact object, which is a neutron star or a black hole, and the ejecta, which is formed by the outer layers of the star. Of course, the star is not that quiet during its lifetime. It loses a lot of mass, which can mean that it can lose the hydrogen or even the helium envelope. So again, through this process, the star again explodes. But now what we have what we had before, the compact object and the ejecta, but now we have a circumstellar medium around the star, or around the supernova better, which has been formed by the previously expelled mass from the star. There are three main types of mass loss in stars. There are the stellar winds, in which the star loses mass in the form of winds, even from the main sequence. We have binary interaction, which the star is in a closed binary with a companion, and the companion accretes mass, removing the envelope or some of the envelope or the outer layers of the star. And then there is the eruptive mass loss, which is mostly the focus of this paper, in which the star loses suddenly a significant amount of mass, mostly during the later stages of the stellar evolution. There are quite many scenarios of eruptive mass loss, but I will I will talk more about the pulsational pair instability mechanism, in which we have, or the theory says that we have a star which is around 30 to 65 helium core solar masses. So this satisfies the criteria in the core for the production of electron-positron pair. So this releases or loses some energy due to this production, and the core contracts, which means the density and temperature is increasing. And this triggers explosive burning of carbon and oxygen. And this explosive burning releases energy enough to remove some of the outer layers of the star. So depending on the mass of the star, these pulses can happen more than one times, or if not, then the star again goes through the same channel I showed before. But now we have the formation with this way of multiple CSM shells. So depending on how many pulses, we can have multiple CSM or multiple layers that have been ejected. And all this, as you can probably imagine, reflects on the type of the supernova that we will observe. And this is a schematic of the types of core collapse supernova. So there are two main types of supernova. Is if there is hydrogen or not in their spectrum. If there is, it's called type 2, and there are also different subgroups depending on how broad are these hydrogen lines. If they disappear, how does the light curve look like, and etc. And then there is the type 1, where we do not see hydrogen in its spectrum. Again, there are different subgroups depending on some other elements that we might see in the spectrum. But I will not focus here, but I will focus in these two sides of this schematic, which we have something that it's called a superluminous supernova. Again, they are classified as type 1 or type 2, depending on if they have hydrogen or not in their spectrum. And again, type 1c, 1b, depending on if they have the presence of other elements. But what is a superluminous supernova? So there are transient events that are very luminous, 10 to 100 times more luminous than the typical supernova. And here we see a plot of a comparison of the light curves of superluminous supernova with the normal core collapse supernova, or the normal type 1, to be more precise. So we see that they're quite bright, brighter than roughly -20 magnitude at peak. And their light curves are longer. So the time scales are quite longer, and actually we have observed superluminous supernova with the rise time of 125 days. And they're also quite rare events. The big question we want to answer in these particular objects is what powers them. So we know that the typical supernova are powered by the radioactive decay of nickel and cobalt-56. But we can estimate the mass of the nickel from the peak of the light curve. And from the superluminous supernova, we have seen that it requires a very high mass of nickel to be produced, that we know that it cannot be produced during the core collapse. So we need to come up with some alternative ideas. And this is some of them. Is the pair instability. So in the pair instability scenario, is pretty similar with the pulsational pair instability that I talked before. But this happens, or is predicted to happen, for even higher mass stars. And in that case, the explosive burning releases energy to completely disrupt the star. And this mechanism is predicted to form the amount of nickel-56 that is required to power the light curves of superluminous supernova. Then there is a magnetar, so the spin down of a very rapidly rotating, highly magnetized neutron star can also give this extra energy. There is the fallback accretion, which is the massive star collapse, forming a black hole, and then mass is accreted within. This can also maybe creates outflows. This outflow can also give some extra energy, and then we have the interaction with the circumstellar medium that I showed before, in which the ejecta interact with the CSM. It creates a shock, which is radiative. So which of these mechanisms powers which superluminous supernova, or if there is one mechanism that powers all of them, is still an open question in the field. But one way of trying to understand what is going on in the stars that explode as superluminous supernova in the late stages, if they lose mass or anything, is by studying their spectrum. So the spectrum of a typical superluminous supernova looks like this. We have a strong magnesium-2 feature at 2,800 angstrom. We have this series of oxygen-2 lines at around 3,500 and 5,000 angstrom. And then we have some weak carbon-oxygen lines in the redder part of the optical spectrum. But today I will not focus in the whole spectrum, but I will focus in this near UV region, in which, as I said, we have this absorption line from the supernova. And then we have this two very narrow magnesium-2 absorption system, which comes from the host galaxy. And this is what we see, or what we have seen so far in the superluminous supernova. But no, recently, or a few years ago, there have been discovered two objects, 16H and 18IBB, which, apart from the features that I showed before, they also showed a magnesium-2, a second magnesium-2 system in their spectrum, which was broader and also shifted by a few thousand kilometers per second. So in the paper of Lunan, who is my supervisor, they interpret this as a fast-moving CSM shell that has been ejected 30 years before the core collapse and has been photoionized by the superluminous supernova. Now, motivated by this, we apply for a telescope time with the X-shooter spectrograph, which is quite high resolution or medium resolution. And we observe 19 superluminous supernova with the redshift more than 0.1. So this cut in the redshift is because we need that part of the spectrum to be within the spectrograph. There is the dedicated analysis of one of the objects in the sample in my paper that was published in that May. And I'm not saying this because I want to promote myself, but I will come back to this later. And then the analysis of the whole sample is an ongoing project, is what I'm working now in my PhD. But the paper that I will present today is about these two objects, that these two objects were the only two objects out of the 19 that they showed this extra magnesium-2 absorption system in their spectra. And here we see the field of this, the field of the sky of these two objects. And this is mostly to see what we really see when we say that we saw a supernova. We mean this, right? Plot that wasn't there before. Before going into the spectra, we should always take a look in the light curve to see if there is anything unusual there in general to extract some properties. So here are the light curves of XGA and XGC. We have, unfortunately, data only in the optical. But from these two plots, we can extract some information and we can compare them with the very well-studied superluminous supernova sample that was published last year. And you can see the comparison in this plot. So here we basically compare the peak magnitude, the rise, the decline, and the color at peak with the superluminous supernova sample, but also with 18 IBB and 16 EH, that were the other two objects that they show this feature in their spectrum. So overall, what this plot says is that the rise, decline, and the color at peak is either consistent with the median or they are placed all over the place. With, of course, 18 IBB be a completely outlier, and this is up to date or is considered up to date the best pair instability candidate. And it does whatever it wants in general. And but I would focus here where this shows that these four objects that they show this line, they are also placed in the brighter side of the distribution, which means these four objects are quite luminous, also compared to superluminous supernova. Now, when we compare the light curve shapes of these objects, again, there is quite a big variety, with 18 IBB doing whatever it wants, as I said before, because it has bumps, it has undulations, it has a lot that we do not really see in our objects. Now, we move to spectra. This plot looks very messy, I can imagine, but I will simplify it a bit for you. So what we see in that plot, or what we want to see, is basically how does our objects evolve overall compared to typical ones. And what this plot says is that they evolve as they expect to evolve. So apart from this particular feature that they show in the spectra, the overall spectra evolves as a typical superluminous supernova. And that plot here, we show a comparison of the spectral evolution of the four objects that show this extra magnesium-2 system. And again, here we see a big variety because 18 IBB, again, it shows some features that we do not see and we do not expect to see in typical superluminous supernova. And the hot topic now is what is going on in the magnesium-2 region or the magnesium region of the spectra. So here is a zoom in to 2,800 or around this region. With green, I have marked the magnesium-2 from the host. And with the gold, I have marked the magnesium-2 that we see, the extra magnesium-2 system. And these are shifted by, on average, 4,000 kilometers per second. So I will make a pause here and I will mention very briefly this. So here you see that we have a doublet magnesium-2 from the host. And this is because this host, either we see outflows or we see emerging. And actually, this is a project that I'm working as a side with some people from the Galaxy Group in my university. And it's not the focus of that talk at all. We use Monte Carlo scattering code that was initially developed by Professor Klaas Fransson. And now I'm trying to make it more user-friendly and updated. So what this code basically does is it gets us an input, some photons from the region around 2800. And these photons are scattered from a CSM shell that has a particular distance and a particular thickness. And depending on the CSM parameters, then we can get some line profiles. So we use this code in order to model the magnesium-2 system that we see in our spectra. And we extract some information about the shells. So here in gray are shown the spectra. Blue, maybe it's not very visible, but the blue is the continuum and the red is the model. So here we extracted what is the maximum velocity of the shell and what is the inner and outer radius of the shell. And from this, we can make an estimate of when the shell was expelled. And we found that it was expelled less than a year before these two supernova go, these two objects go supernova. We did the same for 18IBB in order to see if we are a bit consistent, because in 18IBB paper, they interpret some of the features in the spectra as interaction with the CSM shell. So we did again the modeling and we found that this shell was expelled 9 months before the core collapse. And from this, we can roughly estimate when the ejecta will interact with the CSM. And we found that it will interact around the times that we start seeing in 18IBB these interacting signatures. We can do the same for us, for our object, and try to estimate when and if the ejecta will interact with the CSM. And we found for XGA that it will interact way after we have data. But in XGC, actually, we found that we are expecting to interact around 20 days after peak, but we do not see anything in the light curve or the spectra. So it's not really unexpected this, because in order to see interaction signature, it depends a lot on the density of the ejecta and the density of the CSM. But we start seeing at around 70 days a change in the light curve, which might mean that we start seeing the result of the interaction. But of course, we didn't get any spectra later on in order to see what is going on. Now, when we compare these magnesium-2 features for the 4 objects that they show this, we see that they are quite different. Some of them are deeper, some of them are blended, some of them are narrower. And this reflects to the different CSM properties. So it's not a Catholic scenario that the star expels at a specific time some CSM, and we start seeing this in the spectra. There are various CSM shells that can be expelled, and we see that actually in the spectra. What is worth mentioning here is that in the case of 16E8, after 100 days after the explosion, we start seeing a magnesium-2 emission, which was actually moving from bluer wavelengths to redder wavelengths. And this is because we start seeing a light echo from the shell. And actually at different times, we mapping different parts of the shell. And this can tell us or can give us information about the geometry of the shell. And actually they found that the geometry is spherical. In our cases, we do not have data in order to see if we would have a magnesium-2 emission line or if not. And we cannot say anything about the geometry. But what we can do, or what observers do, is speculate. So can it be a pulsational pair instability supernova? So we think that in order to have CSM shells at these distances moving with velocities of around 4,000 kilometers per second, it's probably a result of an eruptive mass loss. And one of the most popular mechanisms is the pulsational pair instability that I described before. So we did some search in the bibliography comparing with pulsational pair instability models, and we found that we can put a limit on the helium core progenitor mass, more than 46 to 50 solar masses, depending on the paper, because some of them take into account metallicity, rotation, and this, as you can imagine, changes. The geometry could perhaps give a hint of what could be the mechanism, the expelling mechanism, but as I said before, we do not have data to infer anything about the geometry. And of course, the other question that we wanted to answer is what powers these objects? So I gave before 4 alternative scenarios, and here we're starting by investigating the magnetar model, and this is quite common in the community to start with the magnetar model. So we model this with the Redback, which is a model developed by someone who is in our department, and we found that these 2 objects that are that luminous required a very rapidly rotating magnetar with around 10 solar masses of ejecta. So the question now is how a star that is around 50 solar masses explodes, and explodes with 10 solar masses of ejecta. So we start saying, maybe it's not actually a magnetar, but maybe it can be fallback accretion. So we have this massive star collapse, we have the formation of a black hole accreted mass, and this could perhaps give what we want. But the thing is that there are not very accurate fallback accretion models for superluminous supernova in the community right now. And the ones that exist gives that it requires 500 solar masses of accreted mass, which you can imagine is unrealistic. So we cannot really say what type of mechanism could power this, but we have some pros and cons, or we can infer, or we can make questions to ourselves. And now is the time that I will go back to my previous paper. And this is because in that we studied that particular object because it showed in the spectrum 3 very strong prominent carbon lines that we do not usually see in the spectrum of superluminous supernova. And as you can see here in that plot. We interpreted this as that the ejecta interact with the carbon-rich material, which is around the supernova, which is actually attached to supernova. But then later on, these lines vanish, but this one stayed persistent. So instead, we think that this is now not a carbon line, but actually it's a hydrogen line, which gives a schematic of something like this. So in the beginning, we have this scenario, and then the ejecta has expanded and has interacted with hydrogen-rich material. So this is pretty similar to what I talk about today. So we have multiple shells that have been formed. I'm not saying that this is a pulsational pair stability. I'm just saying that we know that there is a CSM shell around this object. And still, we didn't see the magnesium-2 features that we saw in the previous object. So the work that I'm doing now is collecting, actually right now I have started with the whole X-shooter sample and try to use the code in order to model this region and infer some properties for the CSM and try to understand what is really going on in the progenitors of superluminous supernova. Unfortunately, I don't have any results to show because this is in a very initial stage, but I think as soon as this is out, it will be very interesting to really try and understand what is going on in the late stages of the stellar evolution. So here are my takeout messages. We found 2 objects that they show these magnesium-2 absorption lines that I said before. These shells were expelled less than a year before the explosion. And in XGC, we calculated or estimated better that the ejecta will have interacted with the CSM. But unfortunately, we do not have spectroscopic data in order to confirm this. So far, out of 250 superluminous 60 superluminous supernova, there are only 4 objects that they show this. And this already gives a lot of information about what is really going on. It could be a pulsational pair instability that put the CSM shells at these distances, and we can put a limit in the helium core progenitor mass. This is very important because we can try and understand what is going on right before the star explodes and goes supernova. And the analysis of the whole Exeter sample is a work in progress, but I hope it will be out soon. That's it. Thank you.
Thank you. Are there any questions?
Yes.
Thanks a lot. Fantastic talk, very clear.
Thank you.
And very nice work. Congratulations.
Thank you.
I have a couple of questions about the mass that you have derived for the possible ejector.
Yes.
In the magnetar scenario and the mass that you said 500 solar mass.
Yes.
Black scenario.
Yes.
Can you comment on how both were calculated? Which are, how should we believe those two numbers?
That's a very good question. We should believe. So basically, there is the standard magnetar scenario that we use in the superluminous supernova, that we have like the wind, it interacts with the ejecta, wind pulsar, wind nebula, non-thermal photothermalized. So the thing is that we still don't know how this photothermalized ejecta, if this is physical, but the way of extracting actually the ejecta mass is from the rise or from the diffusion times of the light curve. Mm-hmm. And since the diffusion or the rise, it's not that long, it's around 30 days, the value of 10 solar masses is realistic because in our mind, we expect if we have more ejecta mass, the photons take longer to diffuse out. So we would see this in the light curve, or at least this is the
is independent of the fact that there is or not.
No, it's not independent, but yeah, because we take into account opacity, ejecta mass. So yes, it's pretty similar to the nickel power model, but adapted for magnetar. So it's not super accurate, I would say. But the 10 solar mass of ejecta is not unrealistic for the diffusion times that we see in the light curve. But it's not, so if though we say that we are talking about a very massive star of 50 solar masses, then the question is how a 50 solar mass eject only 10 solar mass, where did the rest go? That's why we try to think if it's fallback accretion. There is even worse because we do not really have models for fallback accretion. And depending on the eta, which is basically the ratio, the conversion factor, which still don't know which value is accurate. And depending on that, we find different masses of accreted mass. So we get 0.1, I think. If we get 1, it's completely unreal. It cannot convert everything to energy. But 0.1, it has believed to be something a bit better. But 500 solar mass of accreted mass cannot have a star of more than 500 solar masses. So we know that this is not true, but this is not enough to say that there was not a formation of a black hole. But maybe we need something better in order to understand what is really going on in these scenarios. So recently, actually, a PhD in our department launched some simulations in which you can have formation black hole and successful explosion. And he's working right now on extracting how the light curve would look like. And I think this will be very important because when we talk about supermassive stars, that they do something and then they explode and we see them. So we really need this type of models in the community. My fingers crossed.
Thank you very much.
Yeah, let's see. Yeah, just a second. Are there any students that want to ask something? Supernova students.
No.
Well, if not,
I was just wondering whether the population of superluminous supernovae are found in low metallicity.
Yes.
But then, and these 4 special ones also low metallicity, or
Low metallist. At least this is what we can extract from the host lines.
And then, if you have low metallicity, is it possible that because you have like you say, do you have a small amount of wind loss, then the massive star doesn't lose much angular momentum.
Yeah.
So this massive star keeps rotating rapidly and then becomes homogeneous chemically. And can this be related in some way to the God?
So yes, could be. So in that case, it basically means that you can form a heavy core or a core that could go pulsational pairing stability in a lower mass. And this is actually one of the referees' comments, in which in that case, you basically, is the referee in that room? So basically, yes, in that case, it can, and it should be commented on the paper as well, that you can have, but so this needs a bit of search of, okay, yes, still you can have a bit lower mass, but how lower mass star, even in the amazing scenario of zero metallicity that lose nothing, can have, it can still not be, I guess, like 15 solar mass. It still need to be quite high mass star, I would say. But this needs like to take a look in the models and of the chemically homogeneous star and see.
Yeah, I have just a curiosity. So you said that only for objects have this like double magnetism feature. So do you think there's a bias and we are missing a lot of them, or it's really like super rare and we shouldn't expect that kind of like super massive progenitors?
Yeah. So these questions are will be answered in the paper that I'm doing now. So basically, we need to understand how common they are, because for now we do not really know. Yes, it is true that observed, we have found 4 out of 260, but this can be maybe because we didn't get spectra in that part of the region. Maybe the spectra were noisy. Maybe the resolution of the spectra was not quite nice to resolve these lines. So there are observational limitations that I need to take, that I want and I will take into account now in the analysis that I do. But also, I think, or I have suspicion, that also the luminosity of the object is important, because we saw that these 4 objects are quite luminous also for superluminous supernova. So there must be something also there. But I don't really know now yet, because it's what I'm working on right now.
Let's see next door.
I have a question that maybe it's stupid, but
No.
so you had this example in which you had the 2 absorption features that they become in emission, and then they were shifting.
Yeah. Here.
And then I did not get it exactly. So why this implies spherical geometry? Because I would expect if you have a spherical geometry that if some gas is moving, that you have the shift in both directions, right? But this is only shifting in one.
Yeah. So the thing is, first of all, here, this magnesium, here are not very well resolved. Is not an X-shooter spectrograph. And we are quite lucky that we actually saw these lines here. And actually was the first object that we saw these lines. So these are from the host. These are from the CSM. So then imagine that you have a sphere, that is moving. And yes, it is true that since you have an emission, you have both wings, blue and red, because you receive light from it. But imagine that since this sphere is very big, first you start seeing in the blue side, and then you start seeing the light from behind the sphere, because it takes some time to travel towards you. And that's why we have moving from the redder to the from the bluer to the redder wavelengths, because you see different part of the shell. And this is because it takes time to come to us, because we are talking about the quite, like, distance is quite far away from the supernova. So it's a light echo, basically. You start seeing light from different parts of the shell. And this is only because the size of the shell is quite big and far from the supernova. Another question?
I was wondering if this particular that also. So my question is, if I understood correctly, So you kind of think of mutually excluding the magnetar scenario or the fallback equation around the black hole, right? I think that's just
These are the two that we investigate. Actually, now I'm also running the CSM model in order to see what would be. Yeah, but yeah.
like a lot of people up like a magnet on the fallback. Because I don't see how you would have this, and if you have that, maybe if you have like a rapidly spinning magnetosphere, which interacts with accretion, create some extra outflows, and they might like give you extra energy. I'm wondering if this scenario or if it's a very stupid scenario.
No, it's not stupid at all. The thing is that I'm not expert at all in what is going on in like formation of magnetars, I don't know. But so yes, could be, I would guess. But the thing is that we model what we have available right now. And there are these 4 scenarios because these are the 4 ideas that people came up. There are more people trying to also find a combination of these. But we cannot model it in order to see if that could be a case or not. That's why we explore like magnetar fallback separately.
Thank you very much for the talk. It was really very instructive for
Thank
those of us that don't know about these superluminous supernova objects. About to expand on this question, you mentioned the eta, which I guess it's the accretion efficiency of the black hole,
Yes.
right? So,
The conversion of the conversion of like mass to energy, basically.
yes. However, this is the radiative efficiency that is used.
Yes.
Common. However, if you have these large amounts of masses trying to agree to a black hole, you're going to get mechanical feedback from the output.
Yeah.
That is not related to what's happening to the black hole. So I guess for me it seems that if you want, I'm trying to understand.
Yeah.
So these 500 solar masses is the equivalent mass that you need in order to convert to the energy.
Yes.
However, if there is a modular momentum and you have something close with this, etc., then perhaps you can achieve this this feedback and these energies with a lot less mass. However, I'm not exactly sure if that aligns with the work that people have done in fallback accretion. But for me, this is not like the end game for the fallback scenario. I don't know.
Yeah. No, I completely agree with you. But as I said before, it's like what we have so far for now. But again, I will say I'm not an expert on what is really going on when mass is accreting in a black hole. But I can imagine that, yes, you have some energy, you have outflows, you might have jets as well, that they can all contribute in thermalize the ejecta, giving these values in the luminosity, or what we observe actually. But there are no models to do this or to explore if that could be the case. So I don't know. And I don't know anyone actually who works in a fallback accretion scenario in order to suggest what you just said. But yeah, I agree that could be so much more than what we have now. But that's why we need the modelers. I mean, we just say, okay, these are the data we have. These are the models you provide us. This is what we do. But we need data, we need models. So let's collaborate a bit better.
Thank you.
More questions? Or people online? I don't see any question online.
I don't know. I don't see either. I don't know.
So can I ask something?
Yeah.
If you know, I don't know. Where they model the magnesium lines,
Yes.
what do you know what parameters they considered for the CSM? I mean, I guess density.
No, so you consider a density profile and an optical depth, because it's quite optically thick. But the thing is that you want to leave the model to decide what will be the parameters of the CSM. So depending on the lines, on actually depending on the velocity or how broad they are and the minimum and maximum of the absorption, and assuming homologous expansion, you can extract the inner and outer radius of the shell. The thing is that you extract it related to the photospheric radius. So we go back and try to estimate the photospheric radius at this part of, or at this time that we got the spectrum, in order to say, okay, the CSM is there, and this is the size of the CSM. Of course, there are uncertainties in all this, but this is like a rough estimate. And also, when we are talking about months before core collapse compared to the timescales of the stellar life, then it's not that, it doesn't change significantly the results. Thank you.
So if there are no questions, okay, thank you.
Thank you. I thank you. Oh, hi, people.